26. Nice new marker.
Yay.
And remember,
That's gonna
please,
last.
yeah, we are taping this, so don't get goofy. And I really need you to not get goofy anyway, because,
This is a hard topic?
yeah,
Out of respect.
it's easy to mess up. I don't think it's hard, but it's easy to mess up.
Is this completely new or
Graphing rational functions. It'll seem more new to you, Johannes, because you missed yesterday.
Oh, I was about to ask, is it a continuation?
Isn't that everything we've been doing?
No, you've been graphing polynomials.
But
Oh.
rational functions, isn't a parabola rational?
No. A rational function, as we defined yesterday, is, here's a new way to write it from yesterday, it occurred to me. A rational function is one polynomial over another polynomial. It's one polynomial over another polynomial. It can also be monomials. It can be, so it can be 1 over x is a rational function.
Can we bind them?
Oh, yeah, 'cause it's the constant, yeah.
Yeah, on top it can be. The bottom has to have a, actually has to have an x in it. And we discussed, reminded people yesterday a little bit of things that can't be in a polynomial, like fractional exponents, other things like that, negative exponents.
Yeah.
Yeah,
0 over 0.
0 over 0 can occur.
Pi.
Okay, so graphing irrational functions, first couple of rules.
All integers? Wait, do they have to be integers in a polynomial?
The exponents do.
But
Okay,
not
the coefficients can be anything else, yeah. Okay, 1. Find, there's many different orders and ways you can do it, and some of this is going to be new information, some of it's going to be old. 1 is find vertical asymptotes. That's your first step. I'm going to give you all the steps before we do an example, and some of the steps I have to teach you what's behind it. Find vertical asymptotes, which are zeros of denominator. 1 gets a sub-step A, which is check for buttonholes. Check for buttonholes. Sounds horrible, but if you have a 0 on the bottom and it's also a 0 on the top, you don't have a vertical asymptote, you simply have a point of non-existence there. So 1, find vertical asymptotes, and then under that, check if you find a 0 in the denominator, make sure it's not also a 0 in the numerator. Again, we'll do an example of this. That's step 1. Step 2, I'll start over here. It's going to be involved, is find horizontal asymptotes. Rational expressions have horizontal asymptotes sometimes. They can also have what's called a slant asymptote. So we may have to review polynomial long division today. Here's a deal with a horizontal asymptote. Where a horizontal asymptote is located depends on the degree of each polynomial. What is the degree of a polynomial? Bless you.
It's the highest
Bless you.
exponent.
Highest exponent. Should always be an integer in this case. Highest exponent. Case 1. I'll put this A. I'll keep you consistent in my labeling here.
Will there be a B or can I just skip a line?
There'll be a B. There'll be.
Yeah.
You'll see. I don't know how to depends on how big you write this. Okay, find horizontal asymptotes depend on the degree. If the higher degree is in the denominator. If the higher degree is in the denominator, for example, f of x equals x plus 1 over x squared plus 5. That's an interesting little rational expression there. They're both polynomials. There'd be no vertical asymptotes because there's no zeros in the bottom. But this would have a horizontal asymptote. Because the higher degree is on the bottom, the horizontal asymptote will be the x-axis, or the line y equals 0. So if you have the higher degree on the bottom, y equals 0 is always the horizontal asymptote. This would be an example of that. Any questions on that whole idea, what degree means? I'm going to give you a lot of information today, but I'm going to try and present it in a straightforward manner. Yes?
Sorry, how do you know the asymptote is 0?
I was going to go into that in a minute, but I can go into it on this one. That's a good point. Okay. Here's how you find that's, what is the asymptote? Okay. Make me do it out of order. Go ahead. No, this is actually a better point too. Okay. The horizontal asymptote is what the function is approaching way out to the left or way out to the right. So this horizontal asymptote, let's talk about just out to the right for this example. This is the limit as x approaches infinity. That means as x goes as far out as we can imagine, what does y do? And this is the limit of f of x equals. But I'm not going to put in f of x. I'm actually going to put in
Why did you do that?
the function. Because Janan threw me off with a very smart question.
No, why did you f of x?
Okay, x plus 5. So as x approaches infinity, the top gets very large, and the bottom gets very large. Okay, so that's kind of hard to tell what's going on there. But let's change this a little bit.
Isn't the bottom getting large faster?
Yeah. But let's see what we can do here. Tell me something about this new fraction here. Tell me what I did in between these steps. What did I do?
You divided by x.
Divided everything by x. I multiplied top and bottom of this fraction by 1 over x. X divided by x is 1. 1 divided by x is 1 over x. X squared plus 5 becomes x plus 5 over
Why did
x.
you divide everything by x?
Why would I? I'm glad you asked. Here's why I divided everything by x.
Do we have to keep on writing lim?
Yeah, every single time. It's like leaving out a verb for Mr. Booth. You don't do it.
But you're just showing your work.
Okay, hold on. Now, what is 1 over x? When x gets really, really large, what happens to 1 over x?
It becomes nothing.
Very, very small, goes to nothing. What happens to 5 over x?
That also goes to nothing.
Also becomes nothing.
And then the whole
What
thing
happens to
becomes
1
nothing.
over x?
Becomes nothing.
Hyperbola.
Well, yeah, rotated hyperbole, yes. But as x gets very large, what does 1 over x become?
Become
Very
nothing.
small.
Very small. Now remember, the
So
limit
equals 0.
The limit as x approaches infinity, this is where is this function headed, not whether it gets there or not. We're allowed to stop writing the limit when we perform the operation of answering the question, where is this headed? And from this step, it looks apparent that this is headed to 0.
Oh, because in a hyperbola it never touches the.
Bingo. Bingo. So now, what we have is, by dividing everything by x, I can see that these go away, this goes to 1 over x, and then the whole thing must go to 0. I stop writing the limit when I answer the question, where is y headed as x goes to infinity? Until I've answered that question, I have to include it every time. Okay? Yes?
So when original first problem,
Yeah.
actually one step where you have one step further. We
Yes.
have that. So when you're at that and are we all just supposed to think, oh, divide by x?
No, there are tricks to this. For now, I'm just showing you why. And I'm not going to answer, you're not going to need to do this to answer any of the questions or do this homework. But this is why it works this way. Next year in calculus, you start learning, maybe a little bit, actually a little bit this year, we'll start teaching you various tricks you apply in a situation where you're finding a limit. But for now, I'm just showing you the trick exists, and that's why this rule works. I'm not saying that you have to use it yet. You won't have to do that from scratch yet,
So how did you
unless you forget the rule.
How did you find the asymptote?
Oh, so if as x gets very large, y is headed towards 0, that's a definition of a horizontal asymptote. What is y getting very close to as x gets close to infinity or negative infinity? In this case, it's the x-axis, yeah. So as this function goes out to infinity in both directions, y will get close to the x-axis.
So in a function, you can have the asymptote equal y equals some. It could be horizontal.
Yeah, so we're having
even if
horizontal
the graph isn't.
we're finding horizontal asymptotes.
Oh.
That's what we're doing here.
All of them will be like this.
No.
Okay.
Now, the second case, okay? We're racing this one. Lots of information today. Mostly we're talking about horizontal asymptotes, but
You forgot your limb sign
where?
at the 0.
No, I didn't, because we answered the question, we performed the operation. The limit says, as x is heading out here, what is the function doing? Well, the function is going to 0. In this last step, we answered the question. So that's where we stopped
But
drawing.
it's never equaling 0. It's a completely false statement. It's approaching.
Can't wait to have this conversation in about 4 weeks. So, actually more like 3 weeks now.
You could have verbally destroyed what I just said.
Hopefully. B, okay.
B of 1.
Hopefully.
Now we're still looking at horizontal asymptotes. Okay, B, if you're looking at a rational function and the numerator and denominator are the same degree.
What if?
For example, f of x equals 3x squared plus 5 over 5x squared plus 9x plus 7. Okay? I'm going to stick with what Janan asked about. How do I know what the asymptote is? Well, the horizontal asymptote is the limit as the function approaches either positive or negative infinity. Yes?
Is that 2b?
Yes, this is 2b.
Okay.
Or not 2b. Yeah. Unlike Hamlet, we are going to choose 2b and not go on a suicidal course of destruction in the name of vengeance for our hallucinatory ghost father.
You don't know that.
So to find this horizontal asymptote, I am going to take the limit as x approaches infinity, which means I'm going to ask the question, where does the function head as x gets very large? Now finding a limit becomes almost a more intuitive process. You got to guess the right strategy. We got to guess the right tactic, excuse me. The right strategy is you muck with the fraction until taking the limit will get you an answer that works. Yes, Jana?
Okay, I would think that to graph like rational functions, instead of like doing all the limits, why don't you just find the zeros and plot them?
Well, I'm going to give you, hold that thought. But I'm going to need the asymptotes as well. But give me the, you're not going to plot the limit every time. I'm just going to do it to show you the rule. Hold that thought. Okay. Now in this case, I am going to find this limit. But what I'm going to do is, I'm going to multiply top and bottom in this case by 1 over x squared. So that'll get me 3 plus 5 over x squared. 5 plus 9 over x plus 7 over x squared. So have I correctly multiplied top and bottom of this fraction by 1 over x squared?
Wait, that's what you're multiplying by?
Yeah. Gets rid of the x squared here, gets rid of the x squared here, makes this 5 over x squared.
So it's 3/5?
You can go. So,
Is it always by divided by x?
or not, well there's a bunch of different tricks, but for polynomials, dividing by some x to some power would be how you get this. So this equals, now, Megan, I sometimes call this part of the step, letting the dog off the leash. Okay? We're going to let x go ahead. We're not going to talk about where x is headed. We're just going to say, okay, x is now ridiculously huge. We're going to let it happen. At that point, you stop writing the limit notation, and you say, okay, 5 over something infinitely large is infinitely small. 9 over something infinitely large is infinitely small. 7 over something infinitely large is infinitely small.
Square.
And squared, and all that's left is 3/5. Now that's not the rule, that's how the rule came about. The rule is the horizontal asymptote, which in this case is the horizontal line y equals 3/5, is always going to be the ratio of the leading coefficients. The first two numbers. This is only true if numerator and denominator are the same degree. Okay? So I could look at this and go, oh, they're both x squared, it's 3/5.
What if it was x squared and y squared?
You definitely would not have a function, nor
Oh, yeah.
polynomial, nor rational expression.
So
You
like,
might, it
y
just wouldn't
squared
be in
plus
the
one.
right form.
It'd be really, yeah, it might be able to rearrange it to a function, but I'm pretty sure that one wouldn't. For one thing, if you have y squared and x squared, you've got some sort of conic, most likely, if you can rearrange it. Or a line if they both square. Okay, so the rule is you use the leading coefficient. If you forget the rule, here's a little trick you can do with limits to find that out. Okay, so this is how you find a horizontal asymptote if they're the same degree. So basically, higher degree on the bottom, it's the x-axis. Same degree top and bottom, it's the coefficient, it's a ratio of the first two coefficients.
What about higher degree on top?
I'm glad you asked. Are you ready?
I don't care. Don't ask questions.
Now this one,
Just let him
Are we
not
gonna
have
know
good
how to do
segues.
buttonholes yet?
you did that
We did that
yesterday.
yesterday.
Oh.
Wait, what do you
Okay, so we gotta teach you guys one more thing, and then we gotta put it all together.
What?
Okay,
Oh wait, what's
I'm
up,
sorry,
bro?
what?
3
Oh god.
Didn't we already,
slant asymptotes.
didn't we already talk about those the other day? Like, not,
Yes.
Not yesterday, I mean the other
A while back I did, but I went in more detail on them. Slant asymptotes. I'm gonna intentionally make something up that will probably be,
Hideous.
yeah. Alright, so, example.
Use simple numbers.
F of x, that won't help in this case. F of x equals x cubed minus 8, I actually know how that factors, over, with this I'm going to make sure this doesn't factor with it, x plus 5. Okay? Actually, I'm sorry, x squared plus 5. If you have,
That's just, that's 2, and then if you square root, if you do the square root, but like the third square root.
the factoring pattern on the top, to remind you, is this will break down to x minus 2 times x squared plus 4x plus 6 plus plus 4.
Are you sure?
Yes. That's how this one breaks down. It's not x minus 2 cubed.
I knew,
Yeah.
but I knew that was 2 if you
Yes.
cubed it.
It is a difference of cubed.
Yeah.
Difference of cubes. There's no such thing as square cubing it, but I knew what you meant. Maybe I'll make something up for that. Okay, but that won't help us here. Now, in this case, if the numerator,
Wait, would it just be 1?
hold that thought, if the numerator is 1 degree higher,
Only one?
only 1 degree higher. This only works if the numerator is 1 degree higher.
Is this an A note? Is this
No, this is all under 3. If the numerator is 1 degree higher, you have to find a slant asymptote. And the asymptote will actually be at an angle. It won't be vertical or horizontal. And you find the slant asymptote by polynomial long division. Synthetic division usually won't work. Synthetic division only works if this is a first degree binomial on the bottom.
Like, can we just use like one of the 2 things that we used last week for actual long division?
No.
But then it'll work perfectly, I'm saying.
No, synthetic division never works if it's, there's an exponent here. It only works with this as first degree, like x plus 5.
Oh, right.
It won't work here. So for this one, you have to look at x squared plus 5. What do I have to do with the fact that there's no x squared or x terms in there?
Should we have written down
Really
the x
0.
minus 2 times x squared?
No, that's a refute, but
0x squared.
I have to put in zeros. X cubed plus 0x squared plus 0x minus 8. Okay, what times x gives me x? I just blew it. What times x squared gives me x cubed? X. So this
I
is,
can't see.
I'll try to move down
Are you
here.
serious? We're actually doing
We're
this?
actually doing this.
Wait, is
So
that
this
sup-
is x cubed,
Is that supposed to be 3 or C?
where? That's supposed to be 3.
3?
It's a whole new type of asymptote.
Okay.
Alright?
We've never done this.
Thank you.
You've done
Yeah.
polynomial long division
Yeah.
before.
Have we?
Yeah.
I hope so.
Yeah, we have.
Yeah.
Yeah.
I just
Alright.
don't
This looks too much
remember.
like the box thing.
Okay, now it's different. It's, okay, so this is x squared, x cubed plus 0x squared plus 5x. And you subtract this.
Well, wait, can you explain
Oh,
how
right.
that fast?
Okay? X cubed minus 8, you have to fill in a 0x squared and a 0x term.
Yeah, I get that, but you just stuck it in that 0x cubed
A 0x squared?
squared and the 5x.
Okay, well let me rewrite it this way. Since I don't have it here, I'll rewrite this as x squared plus 0x plus 5. And account for it there as well.
And so you just need to get
You need to put something up here that when you multiply by the first term of your denominator gets you the first term of your numerator.
Okay.
So that's x in this case. Now I subtract, and that's 0,
Wait, but
0.
you didn't do mom yet. You didn't do multiply.
You see, you didn't do
I did
mom
multiply.
yet.
by
Dad,
these.
mom, sister, brother.
Okay, guys. However you learned it, we're not going to. We'll review this in more depth later, but I want to get
wait,
through
just
it.
kidding. Never mind. You're right.
Okay. So this is minus 5x, right?
Mhm.
Bring down the.
Mhm.
Well, now I could bring down the minus 8. And at this point, I'm actually going to stop because
Why is it a negative?
Because 0 minus
0
5.
minus 5. You're subtracting everything in parentheses.
Why are you stopping? What?
When you multiply the first term you picked up here, you chose up here to make the first term go away. You have to distribute that to everything down here, and then you subtract that entire expression in parentheses.
Oh. Right.
So 0x minus 5x is negative 5x. Okay? Now at this point, I'm stuck with what would I multiply times x squared to get something with an x in it?
X to the negative 1.
X to the negative 1, but we're not going to go into negative exponents. So
We
this
also
is
need
basically,
a
this is,
five.
Negative exponents.
yes, once you need there, what you have, thank you, is this is already your remainder. And you're already at this point where it's x plus negative 5x minus 8 over x squared plus 5. That's your remainder. Okay? Now, as x, I'll show you some examples of this tomorrow, but on a computer that'll make it a little easier. Based on what we just did, see if you can make this jump. As x gets really, really, really large, what do you think happens to this entire expression?
Goes away.
Goes away because you have the x squared on the bottom and the x on top.
No,
Oh, that means that we
It's
can
also
just
negative.
use the. We can just because the higher degree is in the denominator. So now
Yes.
can we just go back? We can use that and then find the y-axis.
Well, if there are coefficients here, that gets tricky. So you want to work it out to make sure you're getting the coefficients right. If these are both 1, that'll work out nicely. But basically, let me finish the conclusion of this. As x approaches infinity, f of x resembles the function y equals x, your non-remainder part. So the whole function just starts to look like y equals x,
Which is a diagonal.
which is a diagonal line. As you're close to the origin, it'll look like all sorts of other things, as we'll see a little more of tomorrow. But as you go out, it starts to look more and more like this line. And I'll show you a bit of that, maybe today. Maybe we'll show that on the computer. Yes, Parker?
From the fx equals x3 minus, that. From that to our final, is there a trick for the top part, or do we have to just do the...
You have to do the polynomial line division. This was not something where I'm about to show you the shortcut.
I mean, it's not even that long, I'm just
Right.
wondering.
There is a shortcut?
No, not really. I mean, sort of, but because when you get the different coefficients here, I want you to work this out for now, put it that way.
Wait,
Incidentally, well, go ahead, ask.
why can't we do them like we did the other ones?
With the leading coefficients?
Or
I don't know, do you think that'll work all the
what's
time?
limit thing? Where you try to pull out and could you divide everything by x cubed or something?
You would divide everything by x
One
squared.
over x.
And then, wait, this only
Yeah.
works when it's 1 higher? So what when it's 2?
Here's what Ramsey thinks. And hold that thought, Parker. Good question, but
My
hang on to
question
it.
had to do with that, but you just
Hold on.
erased.
Ramsey's on to something that
It's genius.
may actually, well, let's see. For now, tonight I'm going to ask you to do it this way, but I want you to think about this one. Are there any
X
cases...
cubed, 8 over x cubed. Doesn't matter.
No, it's actually x squared because I'm multiplying top and bottom by 1 over x
Oh,
squared.
x squared. No, it's
So
just
in
1
this
over
case,
x.
if I take the limit, these will go away, right?
Yeah,
And I'll get y equals x over 1.
which is x.
Do you think there's any problems with that if you have coefficients here?
Yes.
Yes, I do.
That might not work as well.
No,
You want to make sure.
no.
Try it out. Let me know. Get back to me.
Wait.
Do some experiments.
Never
File a
do
report.
call my people.
All right. Yes, Janan. Well, actually, I'm sorry. Parker, you asked me a question first. Parker, you said, what if this is higher? Like if this is x to the 4th? If this is x to the 4th over x squared, the function will actually start to follow sort of a parabolic.
Okay, what if it's x5?
Then it'll start to follow sort of a cubic asymptote.
And
6.
what if x2 is now x10 and x3 is now x11?
It'll be basically the same thing. It'll follow it.
Wait.
So, but we're only going to do linear asymptotes. We're not going to do parabolic or cubic shaped asymptotes. Yes?
It only works if it's 1 degree higher.
Yeah, if it's 2 degrees higher, your answer here will start with x squared, and the asymptote will actually be in the shape of like a parabola,
Wait,
which we're not going to get into.
would that
Guys,
mean-
no cross
Does
check.
that mean nothing could be inside of it, or stuff could just not go
Well, here's the
through
part.
that line?
Well, here's the part I was going to say for the very end, but I'll mention it now. I think I'm actually close enough to it. Horizontal, unlike vertical asymptotes. Okay, a vertical asymptote you can never cross. The function cannot exist in a vertical asymptotes. Horizontal asymptotes near the origin can often be crossed.
No, they can't.
You just said they could.
But doesn't that?
Or, yes, they can.
Then
No,
why is it an
then
asymptote?
it's not an asymptote.
Horizontal asymptotes are different from vertical ones.
Ah.
Well,
They aren't
Why
yeah,
can't
correct.
you
they're horizontal.
Yes, but there also can,
They
there
aren't-
may be cases where
They're
they'll be
correct.
crossed.
It'll be
Then they're not
crossed.
an
What do you mean
asymptote.
crossed?
You'll see.
Oh, like that, and then there's stuff that like when.
Yeah, it's a little bit of a difference between sort of the idea of a limit.
Wait, so for a cubic or a different, then it can neither
I don't think
cross
it'll work.
nor it
They often
Hold that
cross.
thought for like 2.5 years.
Always
So,
It's not helpful.
all right, we're just not going to come up.
Remember it, okay?
All right, Parker, it's not going to come up in this
You
course.
got it.
You won't
Okay.
note.
All right.
2.5
You,
years.
can you delete the and
Now-
make this-
Yes. Yeah. There's more to. Now I need to do like an example from beginning to end.
Just singing in high school.
Oh, so this is just, this whole thing is how to graph one of them.
Yeah. And the book gives you 7 steps. That's how to find horizontal and how to find vertical asymptotes. There's 2 ways to graph them. I'm gonna do.
Accumulating things in your nose.
That's not accumulating in the nose.
Okay, so there's more to it, guys.
This one now.
Thank you. Okay.
So to find the vertical asymptotes, you just find the zeros of the denominator.
Here's one for an example. Let's see if all the information we can get out of this, based on what we've done the last couple days and what I've told you today. If we do, we're going to graph f of x equals x squared plus x minus 12 over x squared minus 4. Okay? First thing I suggest, check if you can factor, because if you can factor, your life is 1,000 times easier. Everyone should see what the bottom can factor to.
X plus 2, x minus 2.
Very good.
X plus 2 minus.
Okay. What can the top factor to? Down to. What can I break that down to?
X
X
minus-
plus-
X
X plus
4,
4
3.
X
And 4
plus
has to,
4.
4 has to be positive.
Minus 3.
Yeah.
Okay. Now there's a new trick I'm still going to show you in this. It's similar to something Mr. Singer did last year. Maybe it's the same. I'm not sure. Okay. So right now I know it has zeros at x equals -4 and x equals 3. Correct? Because wherever the numerator is 0, it's going to be 0. It has no buttonholes. I don't have to worry about that. The no factor repeats top and bottom.
Wait, what about, isn't there a 0 for 2?
Sanity is.
Those aren't zeros. It has vertical asymptotes.
So wait, the zeros only count to the top?
Correct. Vertical asymptotes are at x equals 2 and x equals -2.
So what are my zeros?
X-intercepts. Same as polynomials. Same as we were just doing. So zeros are determined by the numerator. Vertical asymptotes by the denominator. Buttonholes by zeros on both, which we don't have in this case. What else do we know? We can find out a couple things. The Y-intercept. We haven't talked about this yet today, but yes, question on these two, Janine?
Yeah, zeros.
Okay.
Why don't you do the denominator zeros?
I did do the denominator zeros, they're the vertical asymptotes. You guys have to listen to each other as well. I know it's hard, but okay. The Y-intercept.
But her voice is so annoying.
Stop. F of 0 is, I put in a 0 for the x squared, a 0 for the x. I'm left with -12 over -4, which is +3. So I know this passes through the point 0, 3. That could be helpful.
Wait, point, with 0, 3 or 3, 0?
0, 3.
Because it's y.
It's a y-intercept. I put in 0 for x.
Oh,
X squared goes away.
Yeah.
Everything goes away but the negative 12 and the negative 4.
That's just right.
Okay, so the y-intercept is 0, 3 in this case.
We're not there.
There is a form, remember the sign analysis Mr. Singer had you do on polynomials last year?
Nope.
I didn't think it was necessary on our polynomials because if you know the end behavior and you know if it crosses or turns around, you know whether it goes into positive or negative territory. I think you guys should be ready to move beyond sign analysis on polynomials. However, sign analysis here can be more exciting.
Yeah,
Um,
I don't remember sign analysis at all.
Assuming you do. Okay, so coming over to here now, I'm going to start graphing it, and I'm going to do sign analysis at the same time.
Lord, stop.
Yep, this is all just to do one graph.
Is our homework gonna be
Do I have to
one
do
problem?
homework today?
No, it's going to be, but some of it is just like find the vertical asymptote, find the slant asymptote, find the horizontal asymptote.
Yeah,
It's
no,
broken down. It's only have to graph a couple, but it is.
After
fair
about 10
amount.
years of math.
But you gotta get quick at it.
Why?
Because in calculus, this is like all 1/2 of one problem or less. Okay, I'm going to start graphing, but then we'll do sign analysis on the graph.
Cal-
I'm going to try, this is a little bit new for me. It's different how I've done it, but I think you guys, it'll work better. So pay close attention.
Oh, we're ready to graph now?
As I said, we're going to do some sign analysis on the graph.
What does that mean?
No, I didn't-
Determining where the function is positive or negative.
Oh.
Where the y values are positive or
You just
negative.
said SIN.
No, thank you for asking.
I know.
Okay, let's see. I need to go out, guys.
Be right there.
I'm hearing distracting cross chatter. I need to go out, okay, just to 3, up to 3. Okay, there's my y-intercept, that's the easiest one. My 0, I have 1 at -4, I have 1 at +3. I have a vertical asymptote where the function can't exist. Another vertical asymptote where the function can't exist, there are 2 and -2. Here's what I forgot over here. Horizontal asymptote. Tell me something about the degree top and bottom.
They're the same, so you don't have it.
Leading coefficients are 1 and 1, so I have 1 at y equals 1.
What?
Wait, what?
Oh, because it's 1 over 1.
When it's the same degree, you use the coefficient of the ratio of the leading coefficients.
So you also have a line at 1.
Remember it was like
That is
3
how you
fifths.
did
So,
it before.
Yeah,
Yeah,
it
no,
is.
that's it is, because remember it was 3/5.
It was 3/5 when you started out with
This is
3x
so
squared
messed
over
up now.
5x squared.
Oh.
Okay?
Wait, so what happens?
There's a
that?
horizontal asymptote there.
Why is it there?
Because, remember, if I were taking the limit
yeah,
as this
okay.
approached 0, I would do 1 over x squared.
Mm-hmm.
But the pattern always works out that it's the coefficient of I keep saying it backwards, the ratio of the leading coefficients. Yeah, so that's 1 over 1.
That's
So,
okay.
So I've got this horizontal asymptote here. So this is y equals 1, this is x equals 2, this is x equals -2. Okay, now, sign analysis.
Is this a ballerina or?
It's none of the above for these. Okay,
Yeah.
sign it out. We have to know whether it's positive or negative in each interval created by interesting points on the x-axis. And our interesting points on the x-axis are our zeros and our asymptotes. So here's -4. Put a number below -4 into this, and what are you going to get? If I go below -4,
So
Like
negative.
negative
Negative
5.
16.
I'm going to have to do some erasing here. This, if I go below -4, this will be negative, right?
Mm-hmm.
What will like -5 minus 3, positive or negative?
Negative.
-5 plus 2, positive or negative? -4, -5 minus 2, positive or negative?
So it's positive?
Negative times negative over negative times negative means over here it's positive, and it is heading towards a value of y equals 1.
How do you know that?
That it's heading towards that, that's the definition of a horizontal asymptote. It's heading towards that. I don't know or care how
So is the
fast
other
at
one
this
doing
point.
the exact
One
opposite?
head that way?
How do you know it's going
One
left?
head that way? Yeah, that's what I'm saying.
No, because, okay, good point. The question I was asking is how is it behaving for -4 on down? For negative numbers that are to the left of -4 in the number line. So if you plug in -5, here's the rule. it's going to stay the same sign, SIGN, positive or negative, in between each of these intervals, from the zeros to the asymptotes to the asymptotes to the zeros. So if it's positive for any point here, over here, it's positive the whole time. Okay? Now, between -4 and -2,
-3.
Down.
it looks pretty obvious from the drawing that it's going down, but let's double check with the sign analysis. Make sure it's not sneaking and turning around on us somehow. It shouldn't be. But if we put in -3, is this positive or negative?
Positive.
Put in -3, -3,
Negative.
-3,
Negative.
-3.
Negative.
So negative over positive, it will be negative, so it must be heading down towards this vertical asymptote everywhere in that interval. It's got to be negative everywhere between the -4 and the -2. All right?
And
Now, what's it doing between? Well, here's a relatively easy one. Okay? What's the easiest thing to plug in between -2 and 2?
3.1.
0. Yeah, pi, right? And anyway, pi over 2, 1.57. But we already plugged in 0, it's positive. That means it's positive everywhere between -2 and 2.
So it's going up. all the
So
way.
from the Y-intercept, it must keep going up
this
forever.
is like this is sort of reminiscent of one of the
Trigonometric functions, the reciprocal ones like the secant.
That's what I was thinking.
yeah.
This part very much is, although it'll have a different curvature. It won't line up perfectly with
It's
it.
not like a parabola.
But I mean especially
It is a parabola because it's two like square root functions.
Except parabolas don't keep going on forever, and secants snuggle up to asymptotes.
Why is it not parallel?
Oh, you mean symmetrical?
Symmetrical.
I mean especially since it's like
They
one
rarely
graph.
are. They'll only be symmetrical if you have
Oh,
like difference of
plus
squares
4
top and bottom.
plus
I have
minus
not
4.
like one.
Yeah, that one gets you something close to it. Now, here at the 3, Ramsey's jumped in his calculator, but if you do this without a calculator, okay, this one's a little bit trickier. Between 2 and 3. Okay, between 2 and 3.
2.5.
What would happen if you put 2.5 in for x, positive or negative?
Positive.
2.5 in
Negative.
here.
Negative.
2.5.
Positive.
2.5.
Positive.
Positive. So it's definitely negative coming up from this asymptote into the 0. Okay?
But it could turn around. So
It could be, let's double
it
check.
can't turn around.
No, it really
It wouldn't
can't.
pass the.
It really can't. It's gonna go, then it's gonna go from here.
Okay.
But you wanna, and so from 3 on up, you can plug in 3 to all of these. If you think about putting in a number larger than 3 into each of these, you'll get all positives.
That's kind of
Are you
It's kind of pretty.
Or
It's
like-
not symmetrical because the zeros aren't symmetrical in the numerator, is what I meant to say. And this would be how you would graph one, and this would also be how you would answer various questions about other ones.
So what exactly did we do yesterday?
We talked about vertical asymptotes and something called a buttonhole that didn't come up today.
Yes. You mentioned.
homework.
Any questions on this? Now, the homework is not to graph a ton of these. It is to graph a couple of them. Some of them are, that's one of the harder ones.
Should the video be stopped?
Sure.
Remember the rules for horizontal
Mr.
asymptotes.
B, do you want me to stop it?
Yes, because yes, go and stop it and I'll put the homework.